Swayam Prabha. Digital India. Educated India.
Okay, so we'll start with today's class. So the topic of today's class would be intermolecular interactions, right? And what I'm going to stress on in this. Up till this point, we have looked at essentially Coulombic force, right, between charges, and how the intervening salt solution would be screening the effect of the charge or the ions from the effect of the electrostatic potential given out by the charge, right. But there are many interactions also which are not necessarily between charged systems. Systems can also be neutral, but still show interactions. Those are essentially your Van der Waals forces or London dispersion forces, right. But before going there, actually I don't think we will be able to make it that far today. What we are going to look up is some specific aspects. For example, we have looked at Coulombic potential right now. What happens if in between the two charges, one is a point charge and the other one becomes a dipole, right? How does the interaction potential change? And then what happens if you have, instead of one dipole, two interacting dipoles, right? What will happen in that case? How will the interaction potential change? Because that's typically the gradation of interactions we should look at before we understand what dispersion forces are all about. So just to recap what we had from last day. So this is what we said. This is a recap of the last lecture. So if you have a planar charged system, then we saw that psi of x, which is the electrostatic potential at a distance x from this charged plane, is equal to, do you remember what it was? Psi 0 e to the power minus kappa x. So there was a exponential gradient, right, or an exponential decay of your charge or electrostatic potential, right, coupled to psi 0, where psi 0 is the potential at the surface of the plane, that is x is equal to 0. That is what we defined psi 0 to be. Then we said that okay, proteins are spherical or assumed to be spherical. So then our system will change to spherical polar coordinates, right. So that is what we used. So then the final expression we got from there is it's psi of r is equal to 1 by 4 pi epsilon 0 q by d of r 1 plus kappa a times e to the power minus kappa r minus a. So this is the final thing we reached at, and here obviously the assumption was r would be greater than a, okay, because this protein is not a point charge, it has a certain dimension, and we are saying the dimension or the radius of the protein is a. So whatever charges you are looking at is beyond a, because at the surface you have this psi of A, which we also derived. Now think about this, if because now the protein has this radius A, if it is a point charge, for example, if the charge is a point charge, then what will happen? If it is a point charge, then A would be what? 0, right? So, no radius. So, that means A is equal to 0, and then psi of r is equal to 1 by 4 pi epsilon 0 q by d times r e to the power minus kappa r, right, because A is 0 now. So, this is for a point charge, right. So, this is for a point charge and this is what we get. So, the one we saw before, the one we wrote down before was a very general solution, right, and now you are being specific, that is you are saying that A essentially tends to 0. Okay. But you see the concept in this case is still captured. Why? Because you look at this psi of r still has a dependence upon kappa, right, and if you only look at, if you do not consider e to the power minus kappa r, what is this? This is essentially like a Coulombic potential, isn't it? It is essentially like a Coulombic potential. So, along with the Coulombic potential, what you are adding is an exponential variation of the charge in the radius, in the radial direction, depending upon kappa, right. So, this is what you really need to remember, right. I mean, definitely the derivations and the concepts behind these derivations or what you get from the final equation. Okay. So, moving on, what we will do is we will start with intermolecular interactions, right. But before that, let me make a couple of points. So, let us talk about 2 points in electrostatics, and I will tell you what 2 points I am talking about. So, how can electrostatics come into picture? There are 2 ways essentially, especially for proteins. We are always thinking about proteins because that is what we are talking about, our biomolecule. The one is classical electrostatics. The one is classical electrostatics. Now, what does this have to deal with? So, in classical electrostatics, remember classical electrostatics deals with charges, attractions, repulsions and all these things, that is what classical electrostatics is all about. So, you can understand, if I change or if we change pH, we can change the charge density on a protein molecule. So, what do I mean by that? Have you guys heard about this term called the isoelectric point, right? So, an isoelectric point, what happens? Yeah, neutral means number of positive charges is equal to number of negative charges, right. So, number of positive charges equal to number of negative charges. Now, why is this isoelectric point so important? Okay, the reason is this. Suppose we change pH. Suppose we change pH. That means either we go to the acidic side or to the basic side. That means either we are moving to the left of the isoelectric point or right of the isoelectric point. Isoelectric point being in the middle because it is neutral. All right. So, what will happen? Based on this, you will increase number of positive or negative charges, right, depending upon which pH you are going to That means if you are lowering the pH, you are essentially protonating, you are increasing positive charges. If you are going to the basic pH, what are you doing? You are deprotonating, that means you are essentially increasing the negative charges. But either way, what you are doing is, when you are moving away from the isoelectric point, you are increasing charge density. Now, increase of charge density has a very destabilizing effect, on the folded protein, on the folded protein. Okay. Now, what do I mean by that? What I mean is, remember, a folded protein is a compact protein, right. So, volume is small. When you increase the charge density, that means you either acidify it, increase the positive charge, or you go to the alkaline side, that means increase the negative charges. What will happen? If you consider that the protein is not getting affected for the time being, then it will start increasing the amount of either negative or positive charges on the protein, but the volume of the protein is small, right, and you are increasing the negative and positive charges now, because you are moving away from the isoelectric point. So, what will you give rise to? You will give rise to repulsive interactions between like charges, right. So, that means because of this you give rise to repulsive interactions between like charges. Now, because folded protein is compact, it is a folded protein, it is compact, this increase or decrease of charges leads to a huge increase in charge density, right. So, what do I mean by this? Charge density is what? Charge density is essentially the number of charges per unit volume. Now, your volume of the protein is not changing, that means I am saying that the protein is remaining in the folded form, but you are increasing what? The number of like charges. So, how will the protein respond? The protein will try to respond by getting rid or trying to get rid of the repulsions between the like charges. So, how can the protein get rid of the repulsions between the like charges? It starts opening up, that means it starts increasing its volume. So, that means it has to get rid of the excess repulsive charges. So, that is why the moment you unfold a protein, the volume increases, hence the charge density immediately what? Decreases, right, and hence the protein opens up. So, then because of increasing charge density, protein or folded protein is destabilized. Your folded protein is destabilized, right. So, what does it do in return? In return, what it does is relieves itself of the excess charge density by opening up, that is going more to the unfolded form, unfolded or denatured form, and denatured form has more volume, hence it leads to less charge density. So, in effect, if someone is going to ask you, tell me in one sentence, what does a pH induced denaturation mean, or how does it happen? It simply happens, or why does it happen? It simply happens because the protein where does it go? It goes to a lower electrostatic free energy, because if it is in the compact form, its free energy is increased, right, because there is so much of repulsive interactions. So, because of this increase in pH, it tries to go to that point or that system or that state where the electrostatic free energy is lowered. So, that means protein moves towards lower electrostatic free energy, and this is essentially your unfolding of the protein. Is everybody clear about this, right? So, this is another way of trying to think about pH induced denaturation of a protein. See, it's essentially based on charges, right, and this is why it happens, because the protein has to respond to whatever charge density it has and try to lower the free energy, because that's free energy is what all about. Now, that is one. Then there is one more. I said two, right? Then the second one is specific interactions. Second one is specific interactions. Okay. So, what do you mean by specific interactions? I am sure you have heard of this term, salt bridge. Have you heard of salt bridge, or also known as ion pair interaction? Now, if I ask you this, do you think this salt bridge or ion pair interaction is the most dominant force in protein folding? What do you think? Yes or no? Do you think it is? Someone is saying no. How would you prove that it is no? See, there was a time where people thought that these ion pair or salt bridge interactions are the ones which are the most dominant feature, before this hydrophobic effect was not that well known. But the problem is this, the thing is, the question we are asking is this the dominant force, is this the dominant force for our protein to fold? How can we think about this? Let us try to argue this fact. Let us consider a 150 amino acid protein. Let us consider 150 amino acid protein. When people looked at the structure of the protein, what they saw was they had only 5 salt bridges. In the 150 amino acid protein, they had 5 salt bridges. 5 salt bridges means out of 150 amino acids, only 10 amino acids are actually involved in forming the salt bridges or ion pair interaction. The rest 140 are not. Hence, in terms of the number of amino acids involved in these interactions, don't you think it is too small to become the most dominant force? So, this is how people argued against the fact that it should not be the dominant force, because see, people were trying to rationalize, right, why proteins fold and what are the forces behind it, and then this is one of the ways. So, they look at the number of interacting pairs present and they saw there are 5 pairs, 10 amino acids, which is too small for a 150 amino acid protein to fold only based on that ion pair interaction, right. So, there must be some other issues going on. But anyway, so the idea was these are two types of interactions, one is a classical charge interaction and the other one is specific between the respective ion pairs which are forming the salt bridges, right. So, this is what about classical electrostatics, screening, Coulombic potential and all these things. Let us try looking at something else. What we are now going to look at is ion dipole interactions. So, as I said at the start of the class, we are essentially talking about charges. Now, we are talking about a charge and a dipole, but before we actually try deriving expressions for these, let us look at what a dipole means. So, Suppose I have something like this, there is a positive charge, there is a negative charge, right. So, this is plus q, this is minus q, and say the length is L. So, this is a typical dipole, right. So, dipole means at the two ends of the dipole I have similar charges q minus q, right, similar, but separated by a distance what L, right. And then because we have a dipole like this, we are going to have something known as what, a dipole moment, very good. So, the dipole moment mu is equal to q times L, right, it's q times L, where q obviously is the charge and L is the length in between. Where do you consider the length from? It is between the center of mass of the negative charge and the center of mass of the positive charge. So, that is essentially what your dipole is. See, I am not taking it to the extreme ends, I am taking it from the center of mass, right, the center here and the center here essentially. Okay. But remember, dipole moment is a vector quantity, right. Dipole moment is a vector quantity, always remember that, because it has direction. And where does the direction grow? How is the direction like? Right, this is the direction nature of your dipole. Okay, that is why it is a vector quantity. Vector is all about directions, it is not a scalar quantity. But think about this, when you are talking about a protein or you are talking about any molecule as such, a simpler molecule, you will not be having only one dipole, you will be having series of dipoles, right, because you will be having series of bonds where there are atoms connected which have different negativities rather. So, hence they would be giving rise to dipoles each and every bond. So, what I can write is, say suppose if I am writing the dipole moment in the x direction, I can write it is, say I can write say mu I in the x direction is sigma I q I x I. Okay. So, this is in the x direction. So, this is essentially equal to mu of x. What does it mean? So, that means the total dipole moment, so look at this mu of x in the x direction is equal to a summation of what? All the charges, I means the respective charges, right, or the respective these things having the charge q I, and x is the what, x coordinate of that, and you are summing over what, you are summing over all the possible interactions it can have. That means you have one charge and it can interact with many other charges, it can have many other dipoles. So, you are summing over all dipoles in the x direction. But when you are talking about a 3-dimensional system, you are not going to have only x, right, you are going to have what, y and z, right. So, then what I can write is, I can write your total, that is mu y would be equal to sigma I q I y I, right, and similarly mu z would be sigma I q I z I. So, again x, y and z are the coordinates respectively, and those are the directions you are looking at for your dipole moments. So, this mu x, mu y and mu z. If I have these, what is your total dipole moment now? The magnitude. So, I can write based on this, mu is equal to root over mu x squared plus mu y squared plus mu z squared. This is your total dipole moment. This is essentially the square root of the sums of the squares of your dipole moments in the respective coordinates. Okay. So, this is your total dipole moment. Okay, clear? Now, having looked at the dipole, now think what will happen now. Suppose I have a system like this. I have a dipole which is like this, right. So, this is my dipole, this is my dipole, this is a minus charge q1 and this is the positive side q1. Okay. The length of the dipole is L, that means the distance of separation between the positively charged end and the negatively charged end is L, right. Now remember, what were we talking about? We started with what? The ion dipole interaction, right? So I already have a dipole. Now I need to have an ion or a charge. So what I do is I put a charge here. This is a charge, and say this charge is Q2. Now see, they are on the same line, right? It's a collinear geometry. It's essentially on the same line. And then what I tell is, I give you this information that the distance between the center of the dipole and this charge, which is a point charge, is given by r. Okay. Now our idea is find the interaction potential energy V. It is the same as u of r, it is the interaction potential energy V. I am just changing it to V because the dipole moment has a mu symbol, and I just try to avoid symbolisms, confusion between the symbols, because u is very close to mu. So this is what I have to find. Okay. Now how would we do that? You look at the system, your V is equal to, right, this is the dipole now, right. So it has two charged ends. This is a monopole essentially, that means only one charge. How many Coulombic interactions would you be having here? You would be having two Coulombic interactions, right. One is essentially repulsive, which is between this guy and this guy, and the other one is what? Attractive, which is this and this. Okay. So let us look at that. So I can write the first one is what, based on Coulomb law. So between Q1 and Q2 is, say, Q1 Q2 by 4 pi epsilon 0. I am not putting any other dielectric here, I am just taking the permittivity in vacuum. Let us do that, because if you are going to put in another dielectric system in a solvent, then another d would come at the bottom, right. That is the only difference we know. So let us do it like this. Now what is the distance between Q1 and Q2? R plus L by 2, excellent. So what I have is R plus L by 2. Now what about the next one? So this is, you can see this is a positive one, right, because it is a repulsive potential. This one would be minus Q1 Q2 4 pi epsilon 0, then R minus L by 2. Clear? So now what I can write is, I can make it a little more simple. I can write Q1 Q2 4 pi epsilon 0. Okay. Then I can write this as 1 by R plus L by 2 minus 1 by R minus L by 2. Okay. Now once I have this, I will make another approximation now. What I will do is like this. So I will say that then V is equal to Q1 Q2 by 4 pi epsilon 0 R. I will take an R common out of the brackets, then I will write it as 1 by 1 plus L by 2 R minus 1 by 1 minus L by 2 R. Is everybody okay with this? Right? I just took an R common from the denominator, that is what I did. I soon realized why I did that. If this was not present, what is this? This is essentially a Coulombic potential between two charges, right? But immediately you can see now you have an extra term out here. So you know that your interaction potential energy will not be a Coulombic potential energy, because the Coulombic potential energy is already out here, and then you have this term. So it is bound to be different, but how different is it? Okay. Now let us try to simplify this based on this assumption. That means I say that L, which is the length of the dipole, right, is, or the separation of the dipolar ends, so is much less than R, which is the separation of the charge from the dipole, which is the center of the dipole. Now if I do that, what will happen? If I do that, what will happen? Then I can write, so this 1 plus, that means based on this I can write L is much less than 2 R. So 1 plus L by 2 R to the power minus 1 can be approximated as what? 1 minus L by 2R plus the higher terms, but I know my L is much less than R, so I neglect the higher terms. The same thing happens for 1 minus L by 2R minus 1. What should this give me? 1 plus L by 2R plus, you neglect the higher terms. Okay, you with me until that point? So now see how it simplifies it. So I have V is equal to Q1 Q2 by 4 pi epsilon 0 R. Then what is the first term coming to be? 1 minus L by 2R. What is the next term to be? 1. Then I can also again write L by 2R, right? Okay, is everybody following that? So it is essentially 1 plus L by 2R, but I have just removed the brackets and I have just done it 1 minus L by 2R. And what should this give me? So what should give me exactly? So that means V is equal to Q1 Q2 by 4 pi epsilon 0 R. The 1 cancels, right? The 1 cancels and we are left with minus 2L over 2R. So essentially L by R, right, minus L by R. So I have out here is minus L by R, which now comes to be Q1 Q2 L over 4 pi epsilon 0 R squared with a negative sign, okay. Now one thing you have seen which is very evident, it is no longer 1 by R, it is how? It is 1 by R squared. So this one, the interaction potential dies off more rapidly than 1 by R. So 1 by R, remember we talked about short range long range interactions, R to the power minus rho, right. So 1 by R is essentially a long range interaction. When you go to 1 by R squared, it dies off more rapidly, that means you are going to shorter ranges. So think how short the ranges are for your London dispersion forces, R to the power 6 and R to the power 12, okay. Now that is one. Can you tell me how, how we can simplify it further? There is one substitution we can make, tell me quick. You have this, right? What is mu 1 equal to? Q1 into L, right? That is what the definition of a dipole moment was. So then V becomes equal to what? Minus Q2, right? Then mu 1 over 4 pi epsilon 0 R squared. So let me write in a better form, minus Q1 Q2 over 4 pi epsilon 0 R squared, okay. So this is the other difference. One was the R squared. Now before, when we were talking about the Coulombic interaction, you talked about only Q1 and Q2 respective charges. You never talked about dipole moment, right? Because it was a monopole, it was just a single charge. But now you have a dipole moment coming in. Because you have a dipole moment coming in, we cannot just talk about one charge. A dipole has what? How many? 2 charges. So you will be having interactions from both. So we, in that case, replace it by what? The dipole moment of the respective dipole, and that is how your interaction energy changes. Clear? Okay. So if you now go back to the original collinear geometry we said. Now think about this, Q2, right, is positive, Q1 is negative, so Q2 is here. If Q2 had been negative, where would it have gone? It would have gone to the other side. Or if Q1 had been here, or if Q2 had been negative, then this V would have actually been positive. So that is, you have to keep in mind. Okay. Good. Now let us take a very general case. The general case is, see, I am not always going to have a linear geometry. That means I am not always going to have a dipole and then a charge sitting on the same line. Instead, what I am going to have is a more general case. Let us look at a more general case. What I am going to have is a dipole like this, so this is plus q minus q, and I can have a charge out here. So this is q1, q1, and I can have a charge out here which is q2, which is actually at a certain angle theta with the dipole. See, this is the most general case. Why? Because if this q2 comes here, that means collinear, then theta is equal to what? 0, right, because it is a special case of this one, there is no angle between these two. Okay. If this is the case, then what people have shown, or what is known as the electric field, okay, the electric field or the electric the interaction potential energy, I can write as say okay, I can write as V is equal to minus mu dot E. It's minus mu dot E. Okay. Remember, these are vector quantities. If you look at your books, what you would see is these are in bold letters, because these are vector quantities, these are not scalar quantities. Now this is this is V actually, just keep that in mind. Now if it is a dot product, then I can write V to be equal to what? Minus okay, mu E cosine of theta. So you have the angular dependence coming in now. But remember, when we go from this dot product to the scalar product, essentially, what are these quantities? Do you know what these quantities are? They are referred to like these. These are referred to as, these are scalar products, these are referred to as absolute magnitudes of the respective vectorial forms. Okay. So these are your magnitudes. These are magnitudes, right. So essentially the magnitude of a dipole is QL, that is what it is, what do you know. But what you do not know is this E is the electric field, E is the electric field, and this electric field which is given out by Q2, essentially the charge, and this electric field can be written as Q2 by 4 pi epsilon 0 r squared. Okay. Now this can be derived, we will not derive this. So the electric field can be written as, from the charge, as Q2 by 4 pi epsilon 0 r square. Guys, this is not a potential, looking at a field now, okay, it is an electric field. The potential is defined as mu dot E, okay, this is the electric field. Okay. So if you have, this is what E is, now look at the most general form, then your V should be equal to mu, right. Now I am talking about the magnitudes, I am taking out this absolute for symbolism, mu dot E cosine of theta. So that means mu Q2 by 4 pi epsilon 0 r squared cosine of theta, and I am putting in mu 1 out here. So this expression, please remember this expression, is the most general form of the expression when you have your charge at any given angle with the dipole, right. And you can easily realize the similarity between this one and that one. Okay. I can also put a negative sign out, I forgot actually the negative sign, because that is how it was defined. Anyway, the charge will take care of that essentially. So now if you look at these two, so this is what we derived for a collinear geometry, right, and this is what we are now deriving for any general angle, theta can be anything. So under what conditions will this one reduce to this? If theta is equal to 0, cosine of theta would be cosine of 0 would be 1, and hence this would go to this, and that is what we actually had started with. Okay. Good. Now let me see how much time we have. Okay, I will just start this, then we will go on with this in the next class. What I will do now is I will change from ion dipole and I will go to dipole interactions. See, if you understand what you are trying to do, we are trying to slowly go up step by step. That means the first step was a Coulombic point charges. The next is a point charge and a dipole. But now we have done that, we go to a dipole now, right. and later we will come to molecules where essentially you do not have any well developed dipoles, you give rise to instantaneous dipoles, and that is what your van der Waals interaction is all about. But these are all about where molecules already have a dipole built in. Okay? So, now again let us take a very general case. So, that means I have two dipoles like this. So, let us keep this on the same line, let us make the geometry to be collinear. Okay. Let this be q1 minus q1, q2 minus q2. Okay. Well, let this length be L, let the length of this dipole also be L, keeping things simple, and let the distance between the dipoles from the middle of the two dipoles be r, just like we described before. The difference being, in the previous case we had only q2, that means q2, this minus q2 plus q2 had merged on the same point because it was a charge. Now we have separated them, giving rise to dipole. Okay. Now this you have to tell me, if I am going to write V, which is the interaction energy or the interaction potential, how many terms am I going to get? I am going to get 4 terms. Is everybody clear about that? Why? You look at one charge, q1, q2, this positive end, q1 minus q2, 2, right? Then minus q1, q2, then minus q1 minus q2, 2, that means total of 4. So, you can see what has happened. When you were in a Coulombic interaction, you had only one potential, 1, hence you had 1 by r. When you went to ion dipole, you had 2. So, actually you went to 1 by r square. You see how it is slowly falling in place, right? And the reason is, now physically can you reason out why it is decaying so rapidly from a Coulombic to an ion dipole interaction, where it was 1 by r and 1 by r square? So, it is simple, it was only one charge out there, right? But here when you are going to ion dipole, one charge is experiencing actually what? 2 charges now. So, they are scrambling it much more rapidly. Now, when you go to 4, like this 4 interactions, you will be having a essentially much higher interactions in terms of Coulombic interactions with each and everything. That means, try to think about this. If I look at this charge q2, essentially how many interactions would I be having? With minus q2 1, minus q1, and then 1, 3. So, I might expect that it would be 1 by r cubed. Let us see whether we get that. Okay. So, then I can write, what I can write is, I can write V is equal to, say, if I take this one and this one, I can write q1 by q2 4 pi epsilon 0. Now, what should I write? The distance between q1 and q2. Huh? R plus L by 2, are you sure? It shouldn't be R plus L? Are you sure? Check, I am keeping it for you. Okay. Tell me, I will come back, tell me what about between minus q1, okay, what about between say, let us take this as minus. What about between q1 and minus q2? I can write q1 q2 by 4 pi epsilon 0. What is q1 and q2? R plus L, thank you. So, this essentially is R plus 0, which is essentially R, right. So, this is R plus L, okay. Okay. Now, what about this one and this one? Minus q1 q2, you have another one, right. So, I did q1 minus q2, this is attractive, right. Now, I am doing minus q1 q2, minus q1 q2 over 4, right, 4 pi epsilon 0 R minus L. You guys realize this, right. Now, we are looking at minus q1 q2, these halves are L by 2, right. You take that out, you get essentially R minus L. We still have one more term, what is that? Huh? Plus, because see, we did q1 q2, but we have not done minus q1 minus q2, right. So, that will again give q1 q2 by 4 pi epsilon 0, then Is everybody okay with how it was built? So, you can see that is a potential which has 4 terms.
So I think 2 terms more can be added. I think Q1 and Q1 and Q2 with the interaction with Q2.
Between
Q2 Q2 interaction, Q1 Q1 interaction as well there, sir. Because this interaction.
it's a dipole. Which one are you talking about?
Even as the charges are there, Q1 and Q1, 2 charges are there. They have interaction with each other.
No, your dipole moment is taking care of that, right? As mu is equal to q times L. That charge interaction will always be there. But if you're talking about that interaction, then your dipole will never separate, right? It will always be there, and that's what your dipole moment is taking care of, right? It's mu is equal to q times L. That's what your dipole moment is coming in. That's what it will coming in. So that interaction is already taken care of by the dipole moment. That's what I'm trying to tell you. That's why you have this L. Let me go to the final derivation, if I can, and then you will see how it comes through. Okay. So then I can simplify it by writing V is equal to Q1 Q2 by 4 pi epsilon 0. I can take that as common. Then I can write essentially what will I be having? I will be having something which is, I will be having 2 by r, right? I will be having a 2 by r, then I will be having minus 1 by r plus L, and then we are having minus 1 by r minus L, right? I do not think I am missing anything, right? Okay. So, then I do one more simplification. I say 4 pi epsilon 0, I take r out again, and what I do is I get 2, then minus 1 by 1 plus L by r, right, minus 1 by 1 minus L by r. Right. Now, again we take the assumption L is much less than r, but guys, here is this one small problem. The problem is, if I am going to do 1 plus L by r minus 1, what am I going to get? I am going to get 1 minus L by r plus L square by r square and so on, right, negative positive alternating. If I do 1 minus L by r minus 1, what am I going to get? I am going to get 1 plus L by r plus L square by r square dot dot dot. Tell me, why am I keeping the third term too? The L by r terms actually will cancel out. If my L by r terms cancel out, we have to keep those terms until that term which is non disappearing, because if my L by r term cancels out, then we have nothing. We essentially boil down to a Coulombic interaction, which is not true. So, this term is the first non disappearing term. So, as we are seeing out here that 1 plus L by r minus 1, right, it gives you 1 minus L by r plus L square by r square, and as we were discussing, last time when we did it between a charge and a dipole, we did not go to this third term, right, we just stopped at the second term, which is L by r. But here, as you will see, as we just wrote, it is a non disappearing term of the respective expansion. We need it, right, because you will see that L by r and L by r, these would actually cancel out, right, and hence we will need this term. So, writing this one again, what I can do is I can do V is equal to minus Q1 Q2 4 pi epsilon 0 r. I have taken a negative sign out, right, and hence accordingly sign conventions or signs would change inside the brackets. This 2 becomes minus 2, it was positive before, it now becomes negative, and everything else is taken care of. So, here you can see, if I have 1 minus L by r plus L square over r square and 1 plus L by r plus L square over r square, I do that respective thing. What happens is L by r, they cancel out, right, and we are left with L square by r square, L square by r square, because 2 also cancels out with 1 and 1. So, what you are left with is V is equal to minus Q1 Q2 by 4 pi epsilon 0 r, right, times what is the other term we should be having here? 2 L square over r square, right. Now, if I am having 2 L square over R square, now just think about this, how can I simplify it further, right? I can simplify it further by taking this, I can say it is minus q1, right, then I can take L out here, I can also write q2 L out here because we started with L, the length of the dipoles was the same, right. Then this is R squared, right, I have pi epsilon 0 R cubed, this 2 what will happen, it will cancel out with 4, right, and we will left with a term here. So, essentially what I can write is, minus, so q1 L can be written as mu 1, q2 L can be written as mu 2, okay, and hence we have mu 1 mu 2 by pi epsilon 0 R cubed, okay. So, this is the final form of interaction between here, what interaction are we looking at? 2 dipoles. So, you think about the corresponding expression for a charge and a dipole. So, here you can say you have 2 dipoles mu 1 and mu 2, that is 2 dipole moments. When you had a charge and a dipole one, what did you have? You had mu 1 times q, and then there was a cosine theta term which came from the angular orientation. But see, it is very easy to understand. You start going from a Coulomb's law, q1 q2, 2 charges, you go to an ion and dipole. So, dipole will be having a dipole moment mu 1, you have an ion charge q, and then you go to 2 dipoles where you have the 2 dipole moments mu 1 and mu 2. What is happening though is, you can see here it becomes now R cubed. For ion and dipole it was R square, and for Coulomb there is 2 charges or 2 ions, it was R, right. So, that is how your interaction is changing. I mean, that is essentially how your interaction is dying down. So, this is a short range decay, that means you start a short range force, you started from a longer range force which was Coulomb 1 by R, then you move to 1 by R square, then you move to 1 by R cubed, okay. So, this is again your dipole interaction energy, okay. So, dipole interaction energy, right. Now, one thing you have to keep in mind is the same way we did for an ion dipole, we brought in a cosine of theta term. Why? Because obviously you never know that the ion can be at a specific angle with respect to the dipole, right. So, in this case too we will be having a theta term which we will look at in the next class, okay. Thank you.